Okay, hello students. I'm going to try to explain some parts of the lecture that were maybe a bit hard to understand, like how do you actually get the IRMS value for current or voltage, right? So the VRMS value for voltage. Okay, so this will be a couple of part videos. That means to say there will be a few parts. Okay, I will start with trying to explain to you how to do root mean square. Okay, so if you want to find the root mean square for current, how do you go about doing it? All right. Later on, I'll explain to you what is the implication and the use of root mean square. That will be in a separate video. Okay, so today in this video, we'll just focus on the how to root mean square. Right. So the root mean square value of current and voltage, right, generally only applies to alternating currents or voltages. So if we look at this example over here, the current against time graph, all right, this is clearly an alternating current. All right, so the peak value of the alternating current, right, is actually the amplitude of the wave. All right, so these are all terminologies that should be familiar with you from year 4 when you study waves. Right, this is the maximum value of current it can reach uh, from this current. All right, and this capital T here actually represents the period of the wave, which is the shortest possible waveform that repeats itself. All right, so this period here you also learn in waves in year 4. Right, so these terminologies of amplitude and period, right, and if you want to discuss frequency, all these are exactly the same as the wave version of it, right? So you don't have to be too confused about these terms. Right, so this is the amplitude of the current time graph. This is the period of the current time graph, right? So how do we find the root mean square value of this alternating current? All right, so when we talk about root mean square current, right, the actual operation to get root mean square is actually opposite to the order of how it sounds. So it sounds like it's root mean square, right, but actually what I need to do to get the root mean square is I need to square mean root. Okay, and I'll show you what it means by that. Right, so the first thing I need to do actually to find root mean square is to square the graph. So if I look at this graph over here like that, how do I square the graph? I square every y-axis value of the graph, right? So 0 square I get 0, right? So this is the I square value already. So I'm squaring the graph, right? So 0 square I get 0, right? All the numbers here I square, I will get all the numbers here, right? This value, which I call I peak, right? Or sometimes people call this I naught. It's more commonly known as I naught, right? So I'm going to call this I naught, right? So I naught here, if I square, it becomes I naught square. So this value here is I naught square, right? Which is the maximum value for I square, right? So I'll call this I naught square, right? Then following that, I'll come down here, the same thing, I'll square all the values here to get this part of the graph. And again, I get 0 because this part is 0 square. Okay, when you go to negative, right, all the negative values you square, you become positive. So that's why it forms this part of the positive of the graph. Okay, likewise here, minus I naught square, which is this position, right? When you square, it becomes positive I naught square. So this peak and this peak look exactly the same, even though this one comes from negative of the I naught, and this one comes from the positive of the I naught, right? So and so on and so forth. So you see that if I square this graph, I will get this graph, right? And you observe that the period actually keeps its place here, which looks a bit funny because normally period is showing you the uh, shortest time interval in which the wave repeats itself, and this looks like two looks like two periods has passed, but this is not the period of this graph. This is the period of this graph, right? So you need to keep the t here, right? So this looks unusual, but it's correct. Okay, and right, we move on. How do we actually mean the graph? Right, to mean the graph, right, what I'm trying to do is that instead of the current being so awkwardly low at times and high at times, right, I want a value for current that actually uh, represents the average current throughout the time instant. And how do I do that, right? So you can try to imagine it as these are valleys and mountains, right? So mountain, valley, mountain, valley. I want to flatten the whole thing so that it's one horizontal line, and I want to find that value of that line on the y-axis, right? So instead of mountains and valleys, I want a flat ground for the car to run through, something like that, right? So here you need to have a good understanding of the mathematics of a sine square graph. Right, the sine square graph, right? I'm not going to use this version because this version the shape not so nice. I'm going to use an actual mathematical version of the sine square graph, which I copied online. Right. So you observe here, right, the actual shape of the sine square graph is very unique in the sense that the curvature here, right, is actually this way, which actually it's not the same as the original curvature of the ice graph. Can you see the original curvature of the ice graph is pretty steep gradient here, and it's steep from the start. But the I-square graph, right, it actually looks like 0 at the start. In fact, it is 0 at the start, right? So it's a very low gradient that starts to increase gradually, right? So the curvature here is different from the original graph, all right? But if you look at the graph as a whole, the top part looks a bit more similar. What's unique about this is that if I were to look at this I-square graph and I try to flatten the mountain and the valleys, right, I actually can do something like that, all right? I find a line across here such that I will cut this part of the mountain, which is this shape over here. You see this shape over here, and then I fill this valley. Likewise, I cut the other half of the mountain and fill in this valley, another half of the mountain and fill in this valley. And that will force all the mountains, right, to become flat and all the valleys to become higher, right? The level at which I can do this such that it nicely becomes one flat plane is actually half the peak value. So whatever this value is here, in this case is 1, right? If I cut the mountain at 0.5, then it will just nice give me enough material to cover this hole here, and this part enough material to cover this hole here, and so on and so forth, such that the whole thing will become one horizontal line. And this is my mean value. Okay, so to help you understand, I'll give you some numbers, right? So this is, remember, this peak here, this is the I-square graph. So actually this is I naught square. This value is I naught square, right? So let's say I naught square is 8. Where should I cut the mountain such that I can flatten it? Right, if I naught square is 8, I should cut the mountain at 4, right? Because it follows the principle of this graph over here. So if this is 8, what should this value be? 4. If this is 10, what should this value be? 5. Alright, understand? So this value here, where I cut, assuming it's a sine square graph, is always half the maximum value. Okay, so if I naught square here, whatever the value is here, alright, I half this number, I'll get this number. Okay, understand? So with that, I have cut this part over here and chunk inside here. Although, like I said, this shape is not very good, and so on and so forth. So I'll get the half value here, and that's the mean. That's the mean value already. Okay, so this is the mean value, and then after that, the last part is I root. Right, square rooting this is easy. I just square root the whole thing. Then that gives me IRMS. Now, how do I arrive at this relationship in your notes? That they tell you that the IRMS value for a sinusoidal graph is actually the I naught divided by root 2. Okay, I'm going to walk you through the graph to derive this value. Right, so you look at this. Right, if I call this I naught. Right, this value here is I naught. Right, when I square this part here become what? I naught square. Alright, then after that I mean. Right, so this is I naught square. Right, so I remember that this particular shape, you half like that, right? You will be able to form a line here. Right, so the mountain, right, originally was like that. Right, like that. So the mountain was like that. Sorry, like that and like that. Right, then I cut half of the mountain and fill in, cut the other half and fill in, and then become one flat plane already. So if this I naught square, this is I naught square over 2. Right, understand? Right, the same as this is 1, this is half of 1. Right, so this I naught square over 2 now. Then I square root I naught square over 2. What do I get? I naught square over 2. You square root the whole thing. Right, I naught square become I naught. The denominator, you have a 2 becomes square root 2. That's how I get this value over here. That's why this is I naught square over root 2. Alright, so when you find the IRMS value of any alternating current, you have to go through this graphical step-by-step method to actually find out what the RMS value is. Alright, but for a sinusoidal graph, you can memorize that IRMS is I naught over root 2. Alright, and the proof has just been given to you. Right, the same applies for VRMS. Okay, so again, I stress this formula only applies if you know it's a sinusoidal graph. There are other forms of alternating current or voltage. Right, with this, I suggest you try question 7 of the tutorial. Right, I'll try and produce a video solution so that you can see whether you're correct or not.